We start with the second invited speaker. It's a pleasure and an honor to have here Professor Bianca Maria Colosimo from the Department of Mechanical Engineering, Politecnico di Milano. Her lecture is Big Data Mining for Industry 4.0, the new pathway for the digital and green twin transition. Thanks, Laura. Bianca,
Thank you. So I hope you can see my screen, and so I'd like to thank you, the scientific committee, for inviting me today, and I deeply apologize for not being able to be with you in Padova today. I will just spend a few words in some brief introduction of my background, my CV, in just one picture. This is going to explain better what I'm going to talk about in a while. So I should say that I've been always having some sort of bipolar or bimodal, let's say, attitude to research. On the one side, I've been always playing the game in the manufacturing arena, so solving problems with all processes and systems for producing all the parts you are using or buying. And on the other side, I've been always spending sometimes also in trying to solve problems related with data mining and data analysis for quality, which means how we can produce parts that are fulfilling the specification, what we are targeting, let's say, in terms of use, and how we can do that with zero waste, let's say, without wasting too much time in defective parts, especially focusing on statistical process monitoring. And on the one side, I've been, and I will say a few words on the editorial commitment I have in journals that are trying to tackle this problem of dealing with quality data on the one side, and all the association and friends from other universities I've been working with in the last few years. And on the other side, most of the problems I will show are going and are coming from real problems faced by industries. And there are just a few names of connections we are at the current time in Europe, mainly in Europe and Italy, facing, let's say, a lot of problems in solving challenges that are really dealing with complexity. And so we will spend some time in complexity. The last part of this, let's say, slide is just showing that in order for solving problems, I've been funding some labs. So I'm putting my hands, let's say, on real problems by, let's say, driving a lot of, let's say, research challenge using the lab I've been installing in Polimi. And I should say that lately, these two, let's say, polar attitudes I've been always having in my research are fused together by a word that is Industry 4.0, which is also a hot topic at this point in time, that is exactly trying to combine industry on the one side with data mining on the other side. I can just say a few words, and I'd like to mention that I'm past editor-in-chief of Journal of Quality Technology, and I'd like to highlight that we have been spending some time in trying to figure out what is the future of industrial statistics combined to, in this case, new or old, let's say, other types of attitude towards complex problems in quality. And so I just want to mention that we'll be spending some time on a special issue that is out, that is trying to understand better what is the interplay between artificial intelligence and statistics for solving real problems related to quality technology. I'd like to mention also that it is as IISE transactions, we are focusing our attention on the connection between data mining and manufacturing, let's say, in a broad sense. And so this is a special issue that is going to appear in the future. And I'd like also to mention that I'm senior editor of a new journal that is Informed Journal of Data Science that is trying also to face real problems. So I encourage you in submitting nice papers to this new journal, because we are looking for really nice contribution in this area. My, let's say, university, as the one of Laura, is a technical university. So we are just focusing on engineering, architecture, and design problem. I think is the largest technical university in Italy and has a good reputation, let's say, worldwide, especially in the area of engineering, technology, and manufacturing. And this is just to say that clearly I'm just talking about some research results that are coming up from a lot of PhD students and other colleagues that are working together with me. So I will say a few words, let's say, on the lab. Basically, I'm, let's say, co-leading 3 labs. 2 of them, the red side in my small CV, are representing the manufacturing side of my career. The blue labs are mainly focusing on the data mining part of what I'm doing. And so I will spend a few words in saying few examples actually coming out from the ADMI lab, which is a laboratory on additive manufacturing that is focusing on additive manufacturing for metal products. And the newborn, that is the 3D cell lab. It was born 2 years ago together with one colleague of mine in the chemical and material science department that is focusing on bioprinting. I will spend just few words, let's say, on this new direction. IC Labs, it's the lab in which we are trying to show all the approach we are trying to develop for solving real problems coming out in manufacturing and dealing with data. I've been already said something about the role as department editor, but also of journals, let's say my scientific side, in terms of editorial board participation. I'd like also to mention that there's urgent need of strategic and road mapping vision on the connection between data mining and manufacturing. And so this is why I'm also trying to push the idea that we need new solutions, new method, and new people that is facing this complex challenge. I will start, let's say, I will focus my speech basically focusing on 2 keywords, let's say, on the one side. The complexity is the first one. And so I will start saying something why complexity is needed at this point in time. And this is something we are facing in our daily life, especially when we are trying to solve problems related with manufacturing. And I'd like to start with this sentence I like really a lot, because it's just mentioning that when we consider something complex, is that just we feel that it is not easily analyzable, understandable, explainable, or predictable. So the prediction concept is quite interesting and as a central rule in this sentence, in the way that we were used to do it. That is, and this is, I think, also interesting, using the procedures, models, or methodologies that we had at our disposal. So this sentence is basically saying complexity usually something new that we cannot tackle, we cannot face with the existing solutions and the existing tools. And this is why I will show why we need a lot of people trying to solve and develop new solutions, new methods for solving the complexity we are facing in let's say, in the world I'm dealing with, that is focusing on industry and manufacturing. And talking about complexity, usually this is a slide I used to, let's say, also show to my students, saying, what do they have in common, all these products? They are really different products in different sectors. There's something on mobility, there's something on, let's say, consumer goods. There are some implants you can see on the left-hand corner. There's some pasta that has this, let's say, strange shape, or there are some dresses and jewelry. So all these products, the first thing that comes to our mind is that they are complex. They have complex shape. And the second, let's say, connection between all this product, you see there's no unique material, because materials are really different. The size are really different. The unique, let's say, connection is additive manufacturing, because all these products are done with one set of technologies that is called 3D printing or additive manufacturing. And I will spend a few words just describing why I've been spending, let's say, the last 10 years trying to solve problems coming out from using 3D printing and additive manufacturing, as I do believe that this is going to be a new technologies driving future challenges in our world. Okay, additive manufacturing is strongly connected with complexity, as it is said to be a technology that allows us to have complexity for free. This is just a video I hope you can see, where it is explained how parts can be produced. In that case, there was a turbine blade. There's just a powder that is spread out. Then there's a selective melting that is achieved, in this case, with a laser or electron beam. And then another layer, it's spread out, and then the process goes on layer-wise. So it means I'm adding material instead of subtracting material. And this means that at the end, I can arrive to very, very complex shapes with, let's say, no waste of materials, at least in principle. This is why this technology is really going to change the way in which we think about complex shapes and complex products. And in this picture, it's clear what is AM about. I mean, if I'm just considering complexity on the x-axis and cost per part in the y-axis, I can see that all the blue line represent conventional manufacturing technologies. Usually, if you want to create complex products, complex shape product, you need to spend a lot of money. Basically, the cost per part is increasing at an exponential rate. And sometimes you cannot even arrive to some complexity in terms of final shape. While you see that the light blue line, additive manufacturing, is basically creating any type of complex shapes for free, let's say, without any significant increase on cost per part. And this is why complexity is playing a role in using these technologies. I just want to say that technologies are not for just producing parts. And so this, I think, is opening a lot of connection between manufacturing and life sciences, because this is what is called bioprinting. As I was saying, this is the newborn in our lab. It's the lab is called 3D Cell Lab. The free product, the free video you can see are free, let's say, machines that are in our labs at this point in time running for creating what? In this case, what we are 3D printing is living tissue. So we are at this point able to print skin, bones, or living tissue at this point in time that have complex shape, but very simple, let's say, monomaterial use. The key idea in the long-term plan is to start producing organs, and so avoiding all the problem with the transplants of organs, the shortage of donors, and also the rejection problem that you have after a transplantation, because you can use the cells of the patient for bioprinting some tissue that is needed by the patient itself. The main idea is basically to combine living cells inside a bioink, creating a 3D structure that is resembling the final structure, and then start doing your job as tissue engineering or drug screening or research in medical study. We have been start playing the game together with medical schools. In this case, the connection is with Humanitas, and we have been start together making some research on neuronal disease. But I just like to point out that I saw a recent news in New York Times before summer that was just saying that bioprinting is not just a matter of if it's possible or not, but it's just a matter of when, because there was the first transplants of the ear of human cells made by 3D printers. So a patient was using his own cells for having a bioprinted ear, and that was then transplanted on the patient itself. So himself, in this case, it was a lady, so herself. So I think there are new directions that are going from, let's say, traditional products in the aerospace or medical sectors, in the implants, moving really in a new direction that we need to, let's say, try to solve, where we will have a lot of problems to be solved. Going back to my, let's say, the title of my talk, I'd like to point out why complexity is needed for what is an urgent problem in manufacturing, that is the twin transition. Twin transition means basically combining the digital transition that is behind the Industry 4.0 idea, and making also the digital transition and the digital manufacturing a good leverage for moving to green transition. So it means arriving and trying to achieve a better planet. So the two challenges together should be faced, and this is why there's a lot of interest in research in trying to solve this twin transition. I can say a few words on why complexity is needed in the twin transition. And so complexity for digital production, it's really something that can be useful for, let's say, solving a lot of problems. In this case, I'm just showing the sequence of steps where we are using the digital side in 3D printing. So we can start just drawing a file using our computer, so a CAD model that is representing the shape, the complex shape we want to produce, And so spending a lot of time in simulation, computer numerical modeling for describing if the final part is fulfilling the specification and target. Then we can move to a digital twin. So we can start simulating what is going on. And again, we are in the digital side. Then after we are studying this digital twin, so this simulation model that maybe is augmented with real data, we can move to production. And this is where we will spend some time, because in production, the good news of additive manufacturing is that a really open process. So you can see a lot of stuff that are going on while you are printing something. And in this case, there's just some example of video image in the visible range or the thermal range. And so I will spend some time in describing what are the open problems in terms of data challenge when we are dealing with this multi-stream big data mining problem. And then we arrive to the final part, and again, we have a digital problem, or let's say data science problem, because we can analyze the final part using nowadays X-ray CT, and so trying to analyze the final complex volumes in voxels terms, so in small volume instead of pixel. The voxel is a 3D pixel. And again, all these blue dots, I hope you can see them, are just showing small porosities, small voids inside the part after the 3D printing step. And again, we can go back to the design or manufacturing, changing process parameters or changing the way in which we have been designing the part for solving all these defects that are inside the product. Again, modeling the uncertainty of the final shape using X-ray CT is a lot of, let's say, open challenges that the community is trying to solve. Complexity for green. Complexity for green, it's really the big challenge. And I can say that there are a lot of dimensions for using complexity, not just for, let's say, functional performances, but moving green. First of all, let's say, thanks to the design freedom that technologies like additive allows you to use, you can just use materials where it is needed. So it means you can impressively reduce the amount of material you are using for parts. And especially in the aerospace or automotive sector, lighter parts means that you are reducing the fuel consumption. So this is an amazing saving in terms of resources. The other issue is that it's a little bit masked, is that thanks to this complexity freedom, you can reduce the number of components. And this is usually translating an extended lifetime. So you can redesign and use complexity for new parts that are long-lasting parts. So it means that you will spend less time in substituting what you have been producing. You can clearly, again, work on the other side of the world. So when using complexity for producing part, in the example with all the colors that you can see are internal channels in a mold. These internal channels are, let's say, optimizing the thermal exchange of this final mold, and so creating a lot of additional benefits in terms of the quality of the final part you are producing with this mold. And there's a huge change also, thanks to the fact that we can produce when and where it is needed. As I was showing, I can, at least in principle, send the CAD file, the drawing of my part, any place worldwide. So I can now design a part and send this to Boston, and Boston can then start printing the part without any additional need. And so this is totally changing the environmental impact of the supply chain, because in this case, I can just send information rather than components. So it means that you are really having a green impact on the supply chain, because a lot of parts are not traveling anymore worldwide. Clearly, I hope that I convinced you that complexity is needed to move, let's say, for life sciences or the twin transition, let's say, in the way in which we are used to produce part. But on the other side, I'd like to, let's say, point out that there are a lot of challenges related with this complexity that need to be faced from a data science viewpoint. So I will start showing some examples and some paradigm shift, as I call them, that are affecting the way in which we are used to think about quality in production. from the viewpoint of parts, so the complexity of the shape that we have been producing, in line to something that we saw in Laura's presentation before. And then I will just point out that there are an additional complexity due to big data if we are using data that are taken during the process, not at the final stage after the product that's been produced. So when we think to quality data for the, let's say, product viewpoint, we can think about what are the usual way in which we are used, for instance, to do statistical process monitoring. And we have been used to do statistical process monitoring for a long time. And this is usually related to traditional manufacturing. So a simple cylinder or a hole, I can just put out of this feature, which is a shape, just one number, that is the diameter. Even this is a random variable because the diameter has a lot of uncertainty depending on the measurement and also on the production process. But I'm, let's say, using a univariate side of statistic. Then we have been start thinking, okay, maybe just one dimension is not enough. There are a lot of dimensions that are describing this shape, which is even a simple shape that is a simple cylinder, but I need also to take into account the length, not only the diameter, or maybe also some sort of additional feature like the roughness, how smooth is the surface. And so we have been start using multivariate statistics for dealing with quality of a product and trying to figure out if this quality is changing with time. Then little by little, we have been also start having a lot of data. And so we have been able just not to measure diameter or length, but even staying with a very simple shape, start having profiles that are strongly connected with functional data. So I can even take the circularity of this cylinder in one specific section, and I can model how far this circle is for a perfect from a perfect circle that is what I want to achieve. And so we have been start using profile monitoring in the case we are trying to monitor quality with time. And clearly the step to surface modeling is quite easy. Instead of just taking, let's say, the profile shape, we can even think about modeling the whole surface of the cylinder. And this is going to be, let's say, the actual capability we have. Also because having all these data on the final shape, it's easy at this point in time. We have a lot of instruments that can inspect the surface quite easily and quite, let's say, in a very short time. But if you think about the shapes that we are now producing with new technologies like additive manufacturing, really the challenge is going to be a little bit more complex because there are a lot of manifolds of complex shapes, a lot of lattice structures. So I will just present one example of trying to use statistical process monitoring for lattice structure. That is this, let's say, structure that is full of voids. And so I think I have one slide better explaining what is a lattice structure. But the key, let's say, paradigm shift we are facing is that we need to move from simple to very complex shapes. This is some examples of lattice structure. As you can see, these structures are lighter because they are full of void. So it means that I can put material just when it is needed. And they are usually built by replicating one single cell that has a complex shape over and over in a volume. These are simple examples. Clearly, you can even think about changing this single cell geometry in each location or even filling a manifold, and clearly things are going to be more complex. I can just show that this is what all, let's say, sectors, industrial sectors are willing to use because of the good properties of lattice structure for heat exchange, for vibration absorption, or this type of lattice structure is also something that cells like, because it looks like nature, like our bones that are full of empty space, and cells like this type of surface structure full of undercuts, and this is why the lattices are also used in implants. So we start having this problem, say, okay, why should we, let's say, how can we adopt the control chart setting or statistical process monitoring when we are facing these complex shapes? And this is, let's say, an example of where we need, first of all, to reduce complexity somehow, and then we can start using some existing tools or even defining new tools. The example I'm showing is taken from a couple of papers we have been publishing on this topic, and is basically start considering each single cell in this lattice structure as the basic element we want to, let's say, study. Clearly, in this cell, there is just one single cell of this lattice. You can think we are always like competitor as the industrial practice. The industrial practice should be, okay, I can just measure the overall weight or the overall volume of this cell. I know that there are some empty space. I know that there's also some full space, but I can just take out just one number that is, let's call this porosity. So how the volume is filling this regular cell, and then I can start thinking about a univariate control chart, trying to model porosity inside this part. I just want to mention that there are a lot of different open challenges. First of all, the cell is repeating, but it has one specific location in space. So really spatial statistics is going to play the role in this case. In this case, we are considering as an IID, let's say, each cell is like considered as independent, but clearly we can move on and trying to figure out what is also the spatial fingerprint of the process in all this lattice structure. And then there's also an additional problem we have been trying to solve with some colleagues of ours in Georgia Tech. That is, there is also the part-to-part, the within-part variability, each cell inside the part, and the part-to-part variability. Maybe if I'm creating a new product full of these lattice structures, all these cells, maybe there are additional level of variability, let's say. So I'm just saying that there are a lot of, let's say, researchers needed to really solve all the problems that we are facing. But I can start describing how we translate the problem of statistical process monitoring of lattice structure in a functional data analysis problem. And the first thing is that I'm trying to show why this video is basically related with this complex shape. This video is trying just to show what is happening to the lattice structure if we cut this lattice structure at different layers. So it seems like flowers that are flourishing and then stopping again, but it's just a let's say, section of the lattice structure you can see if we are cutting this, ideally, this part with some plane that are all, let's say, parallel to the XY plane. This is what we can do observing the real geometry after X-ray CT, after producing the part and moving to computer tomography to see the real geometry. And we can clearly do the same with the nominal shape. So we can, again, ideally just slice this ideal shape, the nominal shape, and creating this video that is basically a sequence of frames showing the geometry at each single Z level. And so now we are start thinking, okay, maybe we can start considering the deviation of the real part, the real geometry, layer by layer at each Z level with respect to the nominal geometry. And so what you can see now, it's just a video showing the deviation index. Deviation means that I've been putting too much material or less material than needed in one specific location. And so starting from this deviation index sequence of frames, we have been start thinking for one specific cell at one specific Z, trying to compute the overall deviation index. So summing up how much this single cell at one specific Z height it's deviating from the nominal shape. And now you can see that just by following what is going on in one specific cell, we can create a functional data that is basically showing the deviation of that specific cell as a function of the nominal shape, as a function of Z. Just by cutting at different layers this deviation, I can just show the deviation of the cell with respect to the nominal shape is changing along Z. Now it's clear where we want to arrive. I mean, this is a functional data, and so we can start doing the same job for all the cells. And so even in this case, we are in reducing complexity somehow, because now each 3D cell, it's just the functional data, and we can play the game doing all the stuff, or spatial analysis, or functional ANOVA, or any type of, let's say, other approach you may figure out. In this case, what we have been doing, it's basically trying to develop an SPC approach based on profile monitoring solutions. So we have been modeling this profile that is representing the cell deviation with respect to the nominal path as a B-spline, and then we have been basically computing also the residuals, and so we are able to create a multivariate control chart for all these coefficients describing the B-spline, and on the other side, a univariate control chart on the part left that is unexplained, the residual noise. And we have been testing this approach to just see how it works. So we have been basically introducing some defect in one specific strat. So you can see that at one specific cell, the strat is a little bit larger. So there is an excess of material that is at that specific location. Or we can have also, as the example too, a problem in the junction. So it means that the cross between two lattice cells, it's a little bit too large. I've been depositing too material, or the material is not sufficient. And these are the usual way for considering how good our, let's say, lattice monitoring solution is working. So it's the beta error, basically the delay in detecting this problem as a function of the size of the problem, of the size of the defect. In blue, it's our proposed procedure. In red is the competitor solution, in which I'm just taking one number out of a cell for saying that something is good or wrong. As you can see, especially in the case of strat that is oversizing, so the first example, we are really, really fast in detecting the problem instead of waiting a long time or having, let's say, a huge defect before saying something. And this was just by simulation that we have been playing the game with our real lattice structure produced in our lab, and we saw that it's effectively doing the job. So one specific cell was having a really different profile, and so profile monitoring is able to detect this defect. I can maybe move one step ahead, just showing some possible directions for future research. The first thing is that we have been even moving in situ. Instead of waiting of having the final lattice structure that is inspected after the process ended with a X-ray CT, so having the final product in our hand, we decided to move in situ and in line. So just by taking a picture of lattice while they are produced in the machine, we can do again the same type of approach, because it was just developed to be layer-wise, as the AM additive manufacturing technologies used to work, again, layer-wise. And so we were able to show that we can even bring this SPC solution, statistical process control solution, in situ and in line while the lattice is being produced or printed, because we have been showing that by playing a little bit with the uncertainty, and so using some weighted least square solution or weighted B-spline regression solution, we can add a reconstruction in situ that is quite, let's say, good compared with what we can do at the end just by using the X-ray CT. And I want just to mention that we have been started exploring complex shape lattice structure together with the Piercesare Secchi, Shimone, Alessandra Menafoglio, our colleagues in the Department of Mathematical Engineering here in Polimi, for start playing the game with very complex shape on manifolds. I will just complete, let's say, the first idea of what is going to be wrong when we are moving to complex shape for product. And then I move to the second manufacturing paradigm shift that I do believe is going to stay with us for a while. That is moving from product quality to process quality. Again, I've been mentioning this few slides ago. We are really have the advantage of having a lot of data. Really, we are going to have a deluge of data when we are printing something. So we can have a lot of signals, a lot of images, a lot of video image. And so one additional paradigm shift in complexity is that moving from waiting for the final product to be produced and then just looking to the final shape, let's try to move in situ and in line. What are the advantages? First of all, I can stop the process if I see a defect in the first few layers. So it means that I'm avoiding to waste time, energy, material, And also, I mean, this means that especially for the additive manufacturing process that is a slow process, it means that maybe for producing the final part, I've been spending 1 week having at the end a part that is defective, and I should have been able to detect this defect just after a few hours. It's really something. Unfortunately, there's a cons. This is the pros, but I mean, we need to deal with all these data, which are really big. It means it's not just a matter of size; it's also the matter of velocity, and a lot of uncertainties of veracity. So there are all the V on the big data side when we are moving in situ and in line. In this case, I will just show some, let's say, ideas that are always looking and staying in this spatial temporal world. So we need really new solutions for combining the spatial with the temporal side. In this case, for process monitoring, so staying in SPC. I just want to show that there are some data available. So in case you want to enjoy and trying to stay with us, let's say in this adventure, this is the video that is available on and it's related to a paper appeared on JQT a lot of times ago. It's showing the laser that is printing one part on one layer. And as you can see, the laser is going back and forth doing its job. But after a while, there's one part that remains hot for a long time. So I can just go back and show this hot spot. And unfortunately, this hot spot is creating problems on the final shape, especially if you are dealing with complex shape. So this was, let's say, the main problem we tried to solve. We have been using a lot of different approaches. And so I think that there's space for doing better, because clearly there's always space for moving, let's say, one step forward. And this hotspot problem, I think it's quite interesting, but because again, it's considering the dynamic on the one side, but also the, let's say, complex data shape, because this, it's quite different with all the typical problems in SPC related with video image, in which you are observing always one scene and trying to see if something is changing at a given point in time. Because in this case, what is the natural state is that everything is changing. So the dynamic is the natural state and you cannot do anything about that. What you want to detect is something that remains static for a long time. So it's some sort of reverse problem. I just want to point out some new directions we saw in the last few years. That is in trying to model sputters. So instead of focusing on what is going on while the laser is hitting the specific powder, we saw that by just looking what is coming out from this melt pool, that is the sputtering phenomena, can be interesting, even if it's a little bit hard to be modeled, because the sputtering phenomena is strongly related with the final, let's say, mechanical performances and the final performance of these of the part that we have been producing. I'm just showing in this case what I refer to with sputters. So the laser is doing again its job. I'm not interested in what is going on while the laser is hitting the powder, but I'm just interested in observing what is the sputter signature. So that everything that is coming out from the melt pool, this is called the melt pool or laser heated zone. And I can just, with a short picture and simple picture, show that if all the red dots are sputters on a sequence of frames where I've been just putting the laser in the same location, these black dots, and all the sputter signature means that I'm showing what is coming out from the laser heated zone during the video. So it's like staying on the laser. Instead of following the laser that is moving, I'm staying on the laser and just looking to all the red sputters that are coming out from where I am in doing my job of melting the powder. And the first condition on the left-hand side is representative of a sputter signature that is good. So at the end, my part is fully dense, has no pores inside. Unfortunately, when you are moving to some sputter signature that is a little bit wilder, you can experience a lot of pores inside. And so in this case, you want to avoid this condition, because it means if there are a lot of pores inside, the mechanical performance of this part are not going to be proper. We have been again doing our, let's say, experience in our lab, putting a camera that is observing the process and trying to, let's say, obtain high porosity in the final part by just changing what is called the energy density, so the content of energy that we are delivering on the powder. This is showing what is the final density on the final part and showing that there is some sort of the optimization. Clearly, if density is 100%, it means that the part is fully dense, and so it's really good. It's what we want to have. So the 99% or 100% is the perfect part. What is changing on the y-axis is the energy density content from low energy given during the release, during the melting, to high energy at the end. And as you can see, there's usually an optimization going on. So there is one point in which the content of energy is the best you can. If you are putting too low energy or too large energy, unfortunately, you are start having a lot of porosity. In one case, if the energy is not sufficient, you will have these highly regular pores that unfortunately are really bad for the final performance, especially fatigue of the final part. On the other side, if you are start putting too much energy, you have a lot of small pores that are less, let's say, dangerous, but unfortunately, again, you should stay in the optimal condition, which is the condition number 3. And you need to basically being able to detect this condition, which clearly depends also on the material. So we have been saying, okay, how can we model the spatial signature in some clever way? We can clearly use the number of sputters at each frame, and this will be our competitor, and I can, let's say that we are going to beat this very, very simple competitor. At each frame, I'm just counting the number of sputters. We've been trying to do something more. And clearly, there's a lot of, let's say, image analysis that needs to be carried out before. So this is why I will maybe put some emphasis on the need of having some multidisciplinary approach in focusing on manufacturing, because you need to know about manufacturing, about sensing, and about signal and image analysis, because we need for each frame to being able to classify the laser heated zone and the sputters. But after this has been done, we can just follow at each frame the sputter. And in this case, we were just focusing on the centroid of the connected components. And we start having some estimated K function. I think I'm going close to the end, so I will just say a few other words on this example. And unfortunately, I need to arrive to the conclusion because I'm using my time. The way in which we have been modeling the spatial pattern, it's basically using the K function, the way in which we can model special point phenomena. And we have been showing that by using this idea of modeling spatial sputters thanks to this K function, this is going to be very effective in detecting change. Basically, the K function is changing depending on the type of signature you can observe in the spatial phenomena under study. And I think that by using K function fitting and then combining this with a functional novel, again, we have been describing a video image problem dealing with space, with stuttering and with spatial point problem in some sort of easy and reducing complexity modeling with again with the functional data and then using functional ANOVA. And I can just anticipate that this is going to be really successful in detecting any type of problems, and especially being able to detect, this is the key issue, that all the other conditions, when the energy is too low or too different, it's going to be clearly classified with a different K function with respect to the reference level that is what we want to achieve. I have this idea that clearly all these point patterns can be used in many different type of problems we need to face. And so I think that this is going to be possibly the future of, let's say, new direction for dealing with SPC in complex problems. I will skip the problem of using thermal imaging. Again, this is going to be a new direction of future, and maybe if you're interested, we can have a discussion on this additional direction in offline, let's say. I will arrive to my conclusion. And so my conclusion is, should we say something about complexity for the twin transition, and are we ready for moving in this direction? The first thing I want to say is that the transition is full of contradictions. So the first thing is digital is usually against green, because digital transition, computation, and data gathering are energy consuming tasks. So staying in digital side and having a lot of data that are useless is not green at all. And this is just to show the type of, let's say, size we are dealing with just when we are printing for 24 hours something. And if we are taking layer image, we are dealing about gigabyte. If we are moving to high-speed video, we are dealing with terabytes. And if we are moving to thermal video, we are going really in additional one additional order of magnitude in terabytes. This is going to my second, let's say, comment. Big data is not the target per se. So, I mean, it's not that we having a lot of data, a lot of companies are really using this abundance of data as a solution. And unfortunately, having a lot of data is not the key point. The key point is trying to find the right data. So I'm really thinking that we need to move to some sort of dietary data analysis, combining data reduction, sensor, and variant selection. The simpler, the better. I'm also thinking that there is a new direction in edge computing, so I'm moving computation in situ, close to where I'm taking data. And so again, we need simple approach, but effective. And the only way to go is combining the knowledge of the process and the phenomenon of the study. And this is just to let you see that just by moving in the high-speed video for the sputtering in just going in the K-function modeling, you are really reducing the amount of information you need. Last comment, data is not information and information is not knowledge. So we really need to develop new approaches that are robust, that are interpretable, and that are full of knowledge coming out from engineer people and people that are also doing inspection and signal analysis or image analysis for really combining in a successful way. And this is what the companies we're working with are really interested in. Just last comment to say that complexity, maybe it's the old normal that we have been always facing with complex problems since the origin, at least in engineering, but in all sciences. So maybe we just go back to the origin and try to solve the problems by simplifying and trying to find the right way of solving the data deluge. I think it's my last comment for my talk. Thank you.
Thank you very much, Bianca, for your talk. Now I introduce our discussant, Professor Antonio Lepore, Department of Industrial Engineering of the University of Naples, Federico II, and Professor Antonio Canale, Department of Statistical Sciences, Padova. Sorry, Bianca, we have a small problems before with the video, but everything is okay. We can start.
May I ask your microphone if possible?
Maybe you have this one.
I don't know. Okay, can you hear me? Or maybe it can be better with this. Okay, thank you. Oh, I, of course, want to thank Professor Capizzi and all the scientific committee for having built up this amazing scientific program, and of course, Professor Bianca Maria Colosimo for having given us all this amazing point of discussion. I want just to complement his discussion, then there will be no question, there will be just my experience in something that she's warning us to do. Maybe I am one of the engineering guy that she is warning to do some cross-fertilization. And then I want to start with some introduction of the group I belong to. I will be really fast. I'm from an engineering department. I'm from the Department of Industrial Engineering at the University of Naples. And I'm an engineer, and I teach applied statistics to engineers. And I can say that we have a small group that is from the Statistics for Experimental and Technological Research that was maybe founded in the 90s from Professor Pesarin, from a project, yes, of Professor Pesarin and Professor Erto. And we are now having this legacy, and we are then engineers working into the field of statistics. I don't want to waste too much time, but I just want to give a sketch of the ongoing industrial activities that we have to face day by day on a daily basis, and they are in the shipping sector, railway sector, manufacturing sectors. Okay, we have some research outcomes, but the most important topic touched by Bianca is about the reproducibility and the open innovation of the research. Then our output that we like to share to the community are some open packages released on the CRAN. Yes, the big data mining for Industry 4.0 is a new pathway also for the evolution of our role in science as statisticians. I think that the complexity of the problems is really frightening at first when you take it from the real problem. And it essentially then, after the frightening, we have just to move the paradigm from a statistician as a one-man band, as one man with his own computer, to an ensemble that is playing together with others. Yes, my role, our role as applied statistician, I can be very fast, is to gather problems from industry and select those that they may have an impact on the from a data perspective. And then after that, dealing with real data is per se always a big and time-consuming challenge. Then I find myself and all the other engineering guys that are like me with a nice mix between science and data, and then I want to use it to try and formalize the problem, a new industrial problem, in a way that is more structured and accessible to mathematicians, to statistical mathematicians, and to the IT computing, to the IT guys and high performance computing experts, because we also need to do calculations. Then industrial problems we are engaged in represent the very big arena where we develop new methods and models from a general perspective, because we are inspired, we are trying to be inspired by that and identify the broader industrial need. And of course, the statistical gap in the literature, if any. Then, some works from our research group that are in common, that share, yes, the paradigm shift envisaged by the keynote lecture of Bianca is, the first one is the transition from ex situ to in situ monitoring. And we are doing that through functional data, and we are building up some stuff with an old idea that is the regression control chart in a more complex world that is an object-oriented, in this case, functional data analysis. Then we are doing that stimulated by the shipping, the monitoring of CO2 emission and operating condition in the shipping sector. And we use, let's say, we envelop everything in a well-known box for practitioners with statistics that can reassemble by contribution plots and contribution from the original variables. For example, two points that are out of control in one of the control chart in the same use. I'm sorry for time constraints, I can give only graphical abstracts and just sketches of what can be complementary to my message. Okay, but what's the problem here? The problem is to do something that is not on the final individual, not on the final unit, which is the profile produced at the end of a voyage, but during the voyage, what is called in situ. And then we translate it into a real-time problem. And the real-time problem, of course, can be, in this case, maybe trivial, because we can involve warping, very trivial, let's say, registration of the data when we have, for example, a nominal route, as in this case, and projecting time by time in a real time the real route of the ship on this nominal route by giving us, for example, the fractional travel distance that can be used to do that job. But of course, in more difficult case, the warping is very a crucial point. The warping function in the registration of functional data, and we are working on that in these months. And we want to, let's say, embed all this in a framework that is for functional real-time monitoring. And of course, we know that that can be very, very challenging. Then interpretability comes in the talk of Bianca. And what is interpretability? The definition is not very, let's say, there is a lack of consensus about the rigorous definition. But we can say that it concerns the relevant knowledge to support human decision based on the data, based on it. And of course, as statistician, we are for free, we can deliver interpretable model. But in contrast, we have to face also the algorithmic approach of machine learners that sometimes loses this kind of feature that is very important and have positive consequences on the acceptability of any proposed tool and its relative industrial deployment. This was some of the output that came out from a workshop that was organized in Naples, and to which also Bianca took part. And there is going a Springer book about that, edited by me, Professor Palumbo, and from my group, and Professor Poggi from the University of Paris, and authored also by Professor Simon Wood, Professor Seki, and some other guys that works in applied statistics. What we do with interpretability in this kind of complexity? How do we translate practically interpretability, for example, in functional data analysis? We think that one way to address it is to impose to the final solution sparsity together with smoothness. And just to give an example that was inspired by an industrial case study in the resistance spot welding, we have a kind of signature of the process, then process data in situ data, and the challenge is to find out, for example, homogeneous groups of this kind of firm of the technological process that likely pertain to spot welds sharing common mechanical and metallurgical properties. Then this is a functional clustering problem. Data are openly available also on this paper that was edited on applied stochastic models in business and in the industry. But how can we make a step forward to interpretability through sparseness? As we can see here, we are developing a method that can identify the informative and non-informative portion of functional data that make the difference in the clustering. And we can see that here, what is happening is that in the very first part of the firm, we have some information, and on the last part, there is not such information for doing the clustering. And why this is important? Because this optimizes can optimize the understanding of the process and the future data collection and compression towards the green transition, because as we will see, the green transition is made of dietary data and then compressing the data in the most important feature. And open also the topic of active learning that is very, very new. Okay, I don't want to waste my last minutes on how we did it, also on the estimators of the functional linear regression model, but we imposed this smooth. We imposed also sparsity on smooth estimators. We can gain, let's say, interpretability by doing that. We can see the coefficient function of the well-known Canadian weather data, and I just give a graphical abstract also on this other case on Swedish mortality gain, where adaptability, the adaptive lasso gave some results in the interpretability. The last topic is robustness to functional data outliers by using robustness in functional analysis of variance and towards the statistical process monitoring of data that can be contaminated both cell-wise and not only case-wise, which means that you have outliers only in one component and not in the whole multivariate functional observation. Okay, we made simulation, and robustness makes the difference over multivariate models and over non-functional models, but I want to go directly to the end, to the legacy of the talk that we want to bring home. I really thank again Professor Colosimo for this. She, to me, warned the following message: embrace the data dimensionality and complexity, but with parsimony towards the green transition, because the right method can guide in situ data collection, storing, and real-time transfer ex situ, with robustness and integration of existing science and knowledge, as we nicely saw in the first talk from Professor Sangalli, by including partial differential equation and physics-informed approaches. And of course, which is not my very field of research, Bayesian approach. And then I can leave on this the floor to Antonio Canale. Yeah, the third Antonio of the morning. Thank you very much.
Anton. Thank you, Antonio. Thank you, the organizer, for giving me the opportunity to discuss Professor Colosimo talk. I have to admit that I was not aware of her research topic, and I'm really glad to have the opportunity to get in touch with these topics and with this very nice application. And also, of course, I have to thank Professor Colosimo, but for the talk, and of course for giving us the slides with few weeks before, so we were able to prepare ourselves to discuss this. So I'm gonna try to focus on a couple of things that I see, that I saw strongly mentioned in this talk, that are actually, I think, this is my opinion, broad in modern statistics. So the fact that we are facing a paradigm shift in complexity, well, the title of this conference and all the excellence program is about complex data. So I think it's something that is everywhere, not just in industry, but there are many other fields. I think that there are two things playing this game. The one is that the world is complex, and it's always been like that. So this is something that we always had. But the other point is that there are technological developments, and of course the talk was strongly related to the development in technology. So we have this new complex data because we have new technology that is able to do things, very cool stuff. But this also applies in many other contexts, like imagine the medical diagnostic, modern medical diagnostic tools that are able to scan each part of your body in a non-invasive way, or think about social sciences. So the way in which we can study social interaction among people is very different from what was was done 20 years ago, because we have now the data coming from social network, for example. So there are many examples of this. So the complex data comes from the complex world that we are living. This is kind of really complex, but also from the technological development. And the last few years have been an exciting period for statisticians, I think, because in the last year, this growth of complexity has been exponential. So I was almost graduated when Alvarian was saying the notorious quote about being a statistician was the sexiest job for the next 10 years. So now the 10 years passed, but I think that the last 15 years have been really, really exciting. At least they were exciting to me, working as a statistician, because of this increasing complexity and new challenges that the new data are posing to us. I want to quote also a kind of oldish quote, but I think it's very, really modern, by Jerry Friedman, that was referring to the fact that each time the data increase, it was talking about size, but I think that the main challenge is in complexity more than size, and I will go back on this later. We should totally rethink the way we analyze it. So there is a really lot of things to do as a statistician, I think. So commenting on Professor Colosimo talk, the complexity and the green transition. So how can we balance this? We saw that, for example, in the paper on Journal of Politecnology that Professor Colosimo showed us, that if we use a simple off-the-shelf method to process monitoring, we are losing a lot of information. And so this is why she developed with her group a new way of analyzing these kind of things. But there is a dark side of this, which is the parsimony in data management. And so she introduces this idea of dietary data analysis, which I think is a nice thing, but also I think that is something that is very well known in statistics since a long time. So I would say that in multivariate statistics, which is something that was there many years before the big data world or the data science world, it was something that was done. So PCA is a classical example of reducing the dimensionality, reducing the complexity, and work in a easier space, let's say. And there are many examples of this also in modern application with the metric factorization, projection, or embedding, let's say. So I think that is, this idea of data analysis is something really important. And my first question, which I have my opinion on this, but I would like to have heard Professor Colosimo idea, is the whole story of big data probably, this is my opinion, is just a matter of reducing the complexity, reducing the dimensionality, and so work in some simple space. So the real complex thing is of big data is the complexity and not the size. Or maybe this is my opinion. I would really like to have Professor Colosimo's opinion on this. Then, when she was talking about let's say online learning, so the in situ data monitoring, we saw that analyzing a video allows a quicker, more efficient anomaly detection. That's in the piece at the end. And there are many examples. She worked a lot on this in this kind of ideas that we see. We saw a lot of examples of this. We have this idea that data comes as a data stream. So we see the data coming as the data are produced. But my question here is that how we can decline the previous slides with this. So how can we decline this the dietary data analysis? So this parsimony, this dimensionality reduction, also in data collection. So when the data comes into a data stream. Existing knowledge, something that already was discussed in the previous talk and that Antonio mentioned as his last point, is something really that I'm close to. So these data are from a collaboration that I had with the mechanical engineering department. So here they were measuring the traction and the resistance of a biomedical material to make personalized medicine, and they had different ways of producing this kind of material. I'm sorry, I'm not an engineer here, so I don't know all the details, but they knew actually a lot of information about this kind of materials, and they knew, for example, that the control group, let's say that the basic material that we are using, which are the red lines here, we're going to have that particular shape. And all the other things that you see on the bottom were like their new version of the same material. So they knew a lot of things about these shapes of curves. They knew that they were starting at 0. They knew that the slopes were of a given value, and so on and so forth. And so since we really discussed a lot about this, I mean, I totally agree that in many contexts, in industrial, in medicine, in many contexts, we have a lot of information. The point is that how we embed this prior information. And of course, if you talk about prior, the first thing that comes to my mind is Bayesian statistics. And the point here, I think, is not straightforward. Okay, so we always say, okay, we have prior information, let's use a Bayesian approach, but I think it's not always easy to do it. And this comes to a cost. It can be a computational cost, or I don't know. So my question here is particularly focused on the industrial application we saw is, can Bayesian approach be adopted in this context, and which are, in case, pros and cons of this? And then finally, interpretability. So something that is strongly debated nowadays. A lot of modern data analysis actually, or machine learning, or even deep learning, or artificial intelligence, as they are called nowadays, are focused, let's say, mostly on prediction rather than having an interpretable model. Okay, so they use what's depicted here, a black box. So you have a complex big data that enters into a black box, and the nice thing is to have a cool prediction. And so I really, I mean, my question here is the need of interpretability on one side. How is this related to these trends, which are clearly, evident, of using very complex model? A deep neural network is very efficient in producing a reasonable prediction. They're doing wonderful things nowadays, but you don't understand what's inside. So since I noticed that I wasn't aware that Professor Colosimo is also editing a journal on AI and deep learning in this context, I really would like how to measure and how to balance the idea of having something interpretable with something which is clearly a black box, like what falls under the umbrella of deep learning, or let's say artificial intelligence. So these are wrapping up my 4 points. So big data is big in size or complexity, both, but I think the cool things comes in the fact that are complex. About green transition, how can we decline this dietary data analysis, this parsimony in the context of data stream, and then of course knowledge, how to embed this in a Bayesian context. Is it doable? Which are the pros and cons? And finally, this how to balance interpretability with the current trends in like deep black box machine learning algorithms. And thanks, everybody.
Okay,
Thanks. Bianca, unfortunately, given the situation, we cannot have questions from the audience, but of course you have time for the rejoinder to our discussions. So please.
Thank you. I will be really fast. The first thing I'd like to point out, thank you for all the comments, and thank you for this, let's say, very interesting way of discussing about what we have been saying in the last hour. The first thing I want to point out is that the idea of dietary data analysis, it's quite different from the old way of just data reduction. I think there's a lot of new directions to go for selecting data gathering. So what I'm saying is that clearly when you have a lot of data, you can use data reduction in multivariate PCA and all the data reduction world. But now I'm saying, what about changing the data we can gather? So it means, should I use a video? Should I use a signals? Where I have to put sensors? What type of sensors? What is the spatial resolution? What is the time resolution? All these choices are changing the amount of data we can collect, and are clearly then moving also the space for a second step of data reduction. I think that this new idea of data gathering selection and dietary data analysis means just picking the data you need, which means a lot of selection and a lot of problems, clearly, because if you are selecting the wrong sensor, you are losing information on what is going on. I think this is where we need to put some efforts. At this point in time, the idea is just to put sensors everywhere. This is usually not compatible with moving to industry because they want to have some cheap solution. And so I think that statisticians together with engineers should define new way of sensor selection and adaptive sensor, let's say, tuning. This is the first thing I'd like to just to point out on the first point. It's not that I'm just dealing with that existing data. I just need to decide what type of data I want to use and I want to have. Second point, in this case, multiple stream and image. Again, there's one connection with the first thing I was saying. Clearly, when you select a video image or a camera, you can select many different resolution in terms of frequency of acquisition rate. And again, you can decide just to play the game depending on what you really need. So this is moving back to the idea of selecting the type of data you want to focus on. On the other side, what we have been showing, so being able, instead of keeping all the frame and storing all the frame, just keeping the coefficient of a functional data that is representing the core of the image and of the frame. So this is, to me, data reduction. So instead of keeping all the frames in the video for the spatter analysis signature, you can just bring at the end few coefficients of the K function that is representing the spatial process, and this is going to be data reduction. I just want to point out that a very important German company is just asking us to use that approach for reducing the storage of data on the machine. So we are working with companies that want to move on in this direction. So instead of just taking the video image and storing all the video image, doing some clever data reduction depending on the, let's say, information that is contained. Third step, Bayesian. I mean, I've been playing with Bayesian statistics a lot in my past, let's say, when I was post-PhD at Penn State. And I really do love moving Bayesian, especially in the framework of multi-fidelity, because you can connect. There's one side of Bayesian I don't think is needed in this framework. That is, we have a lot of data. So let's say the frequentist viewpoint is fulfilling you with information. It's not that you really need to embrace additional, let's say, knowledge a priori in case it's not really needed. But again, if you're moving to some multi-fidelity approach in which you can imagine different stage of knowledge, the one from expert, the one from simulation, the one from data, in this case, Bayesian can really play the game of creating a natural framework of combining all these sources of information. To me, one key problem is the computational border that I've been experiencing moving for such complex, let's say, multi-fidelity data in the Bayesian side. And so I think that it should be computationally feasible depending on the application you have in your hands. Eventually, black box and interpretability, I should say why, at least from my viewpoint, it has some problem when you are moving to real application. First of all, it's process optimization. When you are modeling something as a black box, or you have a parametric model that is representing what is going on, clearly your knowledge of what is going on is quite different. So usually engineers want to add some representation of the model thanks to the data they can capture to represent what is going on in terms of the basic mechanism, and maybe start also thinking about process optimization. So how can I change and tune the process parameters to arrive to a different objective function or change the process? This is clearly not feasible if I'm using just a black box. Second, trust. I mean, usually when you are saying to the engineers what is going on, having some sort of way of describing what is the model that is representing the data is creating trust, not just interpretability, but also trust in what you are doing, and something that is more reliable, especially depending on the condition that can happen, and more robust if you feel that the relationship between the input and the output are clear and make sense, let's say this way. Eventually, the last point is embedding engineering knowledge. I mean, in a black box, it's a little bit more complex, while all the approach Laura was showing it in the first keynote was just describing that combining existing knowledge by engineers with data knowledge coming from the empirical observation of the process, it's easier if you have some sort of, let's say, white box model or some capability of tuning these two words together somehow. So this is why the interpretability, at least in the world I'm in, is something that is really important. And I think this is the final comment I have. And thank you again for this amazing discussion.
Thanks, Bianca, and we hope to have here very soon. So thanks again. Bye.
Enjoy your lunch.
Bye-bye.